Hey, come on. So hello everyone. Welcome back to the lectures on integer programming. Last time we were talking about formulations and like what are the ideal formulations, what we would like to get from formulations we are getting, and which of them are better, which are worse. This time we're gonna be talking about. We are switching to be talking about the solution of the problems. So once we have formulated them, how do we treat them? What kind of framework we have in order to solve them? But before diving into details, first I want to see if there are any questions regarding what material we have passed so far. Any questions? No questions for now. And second, I wanted to make an announcement about the lectures and their recording. So I am recording the lecture right now. I'm not sure it will be a very good quality of recording. I'm not sure if the technology will allow us to actually record it in the future. So there's no guarantee. So from now on, all of the lectures and discussions are supposed to be in person. But if you for whatever reason cannot make it to the class, it is possible that there will be a lecture uploaded, so you can monitor it online. Okay. So since there are no questions, let's dive in. So what is it? What is it that a solution to an optimization problem really is? So someone might say that it is the value of the optimization problem. In general, people agree that it is actually a couple of things. First, we are interested in finding the feasible solution such that the value, like it attains the best value, and we are interested in finding the best value too. So we actually need to find both. In many cases, it's actually even more that we need from the problem, from the solution. Actually, sometimes if we are given a point, a feasible point, and we are told that this point is optimal, we would like to be able to certify it, to check, to verify that that this is actually true. For example, if we are given a feasible point x in the domain, such that it is actually its value, the value of the objective function at this point is actually superior to all of the other points, like probably subject to some noise epsilon. If we are given such a point and we are claimed that this is the optimal one, we would be interested in obtaining a certificate y hat in this case, such that the gap between the optimal value of the problem and the value of the obtained point is actually verifiable, quickly verifiable if you're given y hat. We'll be discussing it later. What exactly do we mean by by a certificate? But you might already understand what is it that is polytime verifiable. It means that you're able to find an algorithm that runs in polynomial time of the size of the input, such that it outputs you an answer to a decision problem, whether it is an optimal solution or not. Okay. So second, there is a question of whether the solution to our problem is efficient or not. So polytime solution is one approach to define efficiency. However, sometimes it is not enough to solve the solution in polytime. So sometimes you want a polynomial of a certain degree. Some solutions, some algorithms. Actually, we might require the algorithm to actually work in linear time in case we are talking about a big data problem where there is no way we can spend a quadratic time, even a quadratic time to go over all of the possible variants and feasible solutions for the problem. However, for the purpose of for the majority of the course, we will be focusing on algorithms that make polynomial number of arithmetic operations in terms of the size of their input. Then the question is, can all problems be solved efficiently, meaning the all optimization problem? Most probably the answer is no, just because like the intuition is saying that most probably there are easy and hard problems. Moreover, the math is telling us that there are hard problems. I'm not sure we're gonna be discussing in more details about the reduction, the topic of NP hardness. However, if you have heard of it, it's great. So this is exactly what I mean here. If not, that's okay. And first of all, we can read about it in the book, and probably we will spend some time if we have. However, most of the time, there is like such an informal distinction between easy and hard problems. Most probably, if the problem is convex, meaning that the objective function and the constraints are given in the form of convex functions, the feasible set is convex and the objective function is convex, then the problem is easy. There are caveats there because not always this is the case. However, most of the time, if the problem is non-convex, for example, the domain is not convex. A very good example of it is an integer programming problem, because we know that distinct points are not like it does not make up a convex set. Most probably, this like the non-convex problems are hard. If our objective function is not convex, it's also a reason for hardness of the problem. However, also there is a caveat that is telling that usually they are hard, not always. And during this class, from now on, we're going to be interested specifically in the problems which are not convex, meaning they are integer, but still they are easy. We can solve them by attacking them with a certain method. Any questions here regarding the? Okay. So what are the tools in our toolbox? That we can, like, as engineers, what exactly can we do if we are given a problem? First of all, there's different kinds of software to solve problems. They all accept specific formats that are being like passed through them. The commercial there are commercial solvers and there are free solvers that are available out there. The best commercial solvers are basically they're all listed here. How to like what they do and how to access them. We're gonna be looking at details of this in the future. In particular, the next lecture we plan to cover some of it. However, solvers is not all of the complete solution. Before the problem is being passed through the solver, it needs to undergo certain interpretation, like morphisms, changes, and the tool that is doing this is called the algebraic modeling tools. It's basically the IDE and also the programming language that you are using in order to put down your problem into computer. And then this algebraic modeling tool communicates with the solver. So it basically calls the solver in order to solve the problem. These pieces of software are actually distinct, and they are shouldn't be confused. Also, there are commercial and free options for us available. The commercial options are AMPL, GAMS, and AIMF. And the free are normally parts of some other kind of general purpose programming language software. For example, there is one. There are actually several that are built in with Python. There are with Julia and MATLAB as well, and also with other programming languages such as R. It is important to note that in this department in IOR, the official tool for algebraic modeling is actually AMPLE. However, during this class, we will not be using it too much. However, if you are familiar with that and you want to do your homework by using some other programming language, some other tool such as AMPLE, you're free to do it. It's not prohibited. Okay. So we will spend much more time going in depth of how to actually use this tool in the future lecture. On this lecture, I would like to focus on how this solvers, like probably I will not go too much into details how the modeling software works, but I would like to go into details about how solvers work specifically, how they approach the problem, what kinds of guarantees they can provide to us, how we can utilize these guarantees. First of all, the question of proving optimality, right? We were talking about certificates that can possibly allow us to show that a particular point is in fact the optimal one. One kind of certificates of this sort, actually, to be honest, the only kind of certificates of this sort are the bounds. These are the basically the vectors, the pieces of information that can help you recover the upper and the lower bound on the optimal value of the solution. There are two types of bounds: the upper bound, the lower bound, or since we are talking about both minimization and maximization problem, they are normally called the dual bounds and the primal bounds. So if you are solving a maximization problem, then a primal bound is a lower bound on the solution. So let me put it down here. So the primal bound would be the lower bound on the solution, meaning that this is basically the part, like the bound that a primal feasible point essentially would give you a bound. Essentially, if this is called prime, like a lower bound is called primal for maximization problem, just because a primal feasible point does give you such a bound. A dual bound is an upper bound for a maximization problem, just because it's the dualization of the problem that would a dual feasible solution that would give you an upper bound for a maximization problem. If we are talking about minimization problem, the bounds, which basically the dual bound is the lower bound on the optimal solution, and the primal bound is the upper bound on the optimal solution. Are there any questions here about the definitions? Okay. There are multiple ways for us to construct these bounds, and we're gonna be learning about them throughout the few future lectures, actually. So this is just an overview. We'll start by looking at the dual bounds, in particular the relaxations and the theory of duality, and then we'll cover the theory of primal bounds. How can we utilize this? How do we utilize the primal and the dual bounds? Well, if you are given like a lower bound, let's say it's like a primal bound, you're given a value of x that is certifying you that that the value of the optimal value for the solution cannot be lower than for example z3, and you're given a value of y that is telling you that the optimal value cannot be higher than z4. Then whenever you are given like a value, I know z, so let's call it a value a, and it has a value between z4 and z3, you know that it is actually an epsilon far from the optimal solution. And this is essentially how all of these solvers work. They construct that they sequentially construct lower and upper bounds, tightening them to the extent when they actually have bounded the optimal solution, and the distance between these bounds is small enough so that they can actually prove that the solution that they have found is optimal in fact. And having this bounds, having the certificates for bounds, allows you to efficiently recover the proof that a certain solution is the optimal. Any questions here? Cool. Okay. So let's start with the relaxations, but before we do that, let me actually switch my slide deck. Okay. So the first type of bounds that we are talking about are the dual bounds, just because they're easier to explain. So the very basic technique in obtaining dual bounds is a relaxation. What is a relaxation? Well, relaxation is also an optimization problem. So if we are dealing if our main problem is to find maximum of the function f over capital X, the domain capital X, then a problem of finding the maximum of f dash over the domain capital X dash is called a relaxation if the original domain X is a subset of the new domain X dash, and the new function f dash is actually an upper bound for the original function f over the entire original domain X, the capital X. What it basically says is that well, if you had an old domain and there was a function like this, and you wanted to, okay, let me probably let me make it concave instead of convex. Okay, so let's make sure that it is a concave function, and this is our z. So we are optimizing this function over this domain. Our relaxation would be of the form something like a function of with the higher values everywhere, and that is given potentially over a domain that is exceeding the previous one, but at least not smaller. The first nice property of this relaxation is that its value, its optimal value, is always going to be greater than or equal than the value of the original problem. Which is nice, which is giving us the upper bound for the maximization problem, which is the dual bound, which is exactly the thing that we wanted. However, it's important to understand that this is only about the optimal solutions. There might be, like, if you are taking the values of X, if you're taking different like a suboptimal solution, a suboptimal solution of f like the f dash value of a suboptimal solution might be actually smaller than the optimal solution of the original problem. So you actually need to solve this this relaxation to optimality in order to obtain a bound like this. The other property of relaxation is that there are three possibilities when solving a relaxation. First is you have found a relaxation, like the solution to the relaxed problem, and it does not belong to the original set X. Let's say it's somewhere over here. Well, in this case, or let's say that the solution to the original the value of the original problem, or if it does belong to the set X, the solution of the original problem, the value of the objective function of the original problem at the point at the optimal point of the relaxation is not equal to the value of the relaxation at the optimal point of the relaxation. In this case, we have obtained the dual bound, which is the upper bound on Z. So this is the bounding. We have solved a bounding problem. If we have found this as a solution to the relaxation, and it actually does belong to the set, it's somewhere here, and the solution, the value of the original problem and the value of the dual problem at this point actually coincide, so that our relaxation didn't look like this, but it looked like this. So it actually coincided with the original objective function at this point. Then we have solved the original problem, so we do not need to do anything else. So by solving a relaxation, we have solved the original problem. The third case is that the relaxation isn't feasible, and then we know for sure that the original problem wasn't feasible. We also kind of solved it. So basically, we are getting lucky if we are in these two cases, in the cases 2 and 3. However, the reality is that most probably, like most of the time, we're gonna end up in the first option, and we'll have to continue to iterate to find new relaxations, new bounds. Any questions about what a relaxation is, how it works, why it is helpful to construct? Okay, awesome. The first type of relaxation is the linear programming relaxation. Okay, so let's consider a mixed integer program with a formulation of this type, with a formulation P.
Same function, but just relax the so maybe just relax x to x prime, but keep the function at the same.
So you're saying that, let's say that we had this x and we had a function, and if this function is actually given to us on a larger set, we just optimize only over this set. You're saying, can we actually extend this set to include some other points in, like?
Yeah, maybe perhaps if x is like a integer, is a set of integers, so you can relax it to like the continuous.
Absolutely, yes. And this is exactly like, so in this case, our f dash is actually equal to f, but in this case, obviously f dash is greater than equal to f. So it does fall under the definition of the relaxation. That's good. Any other questions here? Okay. So the linear programming relaxation, exactly. We are dealing with a mixed integer program with a formulation P. You remember that a formulation is a polytope, right? So it's just given to us through a system of linear inequalities. This formula, like this, the problem itself can be written as a maximization of a linear function over x's, such that x belong to a domain capital X, which is an intersection between P and some semi-integer set, right? This is by the definition of a formulation. The linear programming relaxation is the linear program where we do not make this, like, basically we drop this intersection. We just say that we optimize over capital X that is equal to P without any intersection with a semi-integer set. Obviously, this new formulation is a linear programming problem. And first of all, as very much related to the previous question. We have the exact same objective function. The only mention that we have made here is we have dropped the intersection sign. The interesting. So first of all, is this a relaxation at all? Is it? It should be, right? Because X here is like was P intersected with something, and since we have dropped the intersection, now X must belong to P, which is exactly written right here. So X does belong to P. This is good. The property, the important property of this relaxation is that for two formulations such that one is better than the other, the solution values are ZP1. So what I want to say here is that if you have two formulations P1 and P2, and you know that this one is actually better than this one, then the bounds. So you remember that we are trying to bound our Z. They're like this two relaxation will correspond to two bounds. The first one is Z1, the second one is Z2. And we know that ZP1 is gonna be smaller than ZP2. So actually they will be swapped around. Z2 is gonna be here and Z1 is gonna be here. So Z1 is always gonna be giving us a better bound that is closer to Z than Z2. So whenever you're doing a relaxation, it is much better to have a better formulation than the worst. Which again explains why we introduced the better and the worse formulations at the first place. There are a couple of examples in the book. Example 2.1, example 2.2. I will turn to them if it's necessary. However, first I would like to come back to the example from the first chapter and consider that. So consider the integer program. We would like to maximize a very simple function of two variables, subject to two linear constraints, and subject to the constraint that the two variables are actually integer. What happens if we ignore integrality constraint? Well, I will remind you that we actually, during our solution of this problem, this point was the optimal one, and this point gives us like some value of the objective function that is going to be the upper bound for our integer program. It is important to understand that this bound is only a bound, and if you are trying to round up or down the value, like the point itself, it won't give you any like anything. If you, for example, were to round up, like round this the components of this factor, you would obtain this point here, which is outside of the feasible effect. So relaxation doesn't really give you any information about the location of the optimal solution to the original problem. It just gives you the bound on the objective function. This is something that is important to understand. However, we will see that people are actually trying to do that, and there are heuristics that are based on rounding up or down, and it does work. But in general, there's nothing the theory that tells us about the quality of this the feasible the optimal solution to the relaxation. Okay, so that, yep.
I was just wondering, you mentioned earlier on a previous slide the three cases. There are three possible
Right.
reasons for relaxation. And the number two is find this. Could you just
It's right here.
Redo the number two one and find a solution, because can you just remind me what that says? Because you said just now that if we find a solution to the relaxed problem, we don't find the solution to the original problem, right?
Yeah.
Okay. And so this, what does this say? We have solved How does that interrelate with the number 2, 1?
That's a good question. Let me state once again what I meant on the next slide. So on this slide, what I'm saying is that the location of the optimal solution to the relaxed problem is not necessarily related to the location of the optimal solution to the original problem. So even though the location of the relaxation is here, the location of the original problem, if I remember correctly, it was somewhere. It was actually this point here. Oh no, it was this point here. This point here is actually the optimal solution to the problem. So you can see that there is actually a significant distance between them in terms of distance within the domain. What this thing was saying here is that if we have found a solution X such that it actually belongs to our original feasible set, the feasible set before the relaxation, and the solution, the value of the objective function, the values of the two objective functions at that point, at that optimal point, coincide, then we have solved the original problem. Let me turn to this example. Let's say that we have changed our objective. Instead of this objective, now we are optimizing minus x1 minus x2. And in this case, our optimal solution is for the relaxation is going to be this point right here, right? Because the 0 is going to be the optimal. At the same time, we know. So this is going to be the optimal solution to the relaxation. At the same time, we know that this point 0, 0 is in fact a feasible point for the original problem, just because it's integer. Moreover, since our objective function between the relaxation and the original problem did not change, we know that in the original problem and in the relaxation, the value of the objective function of the point 0, 0 is the same. Therefore, we have found 0, 0 is in fact the solution to the original problem. I can repeat that again, if that is necessary. That's good? Okay. Yep. Mm-hmm.
We're finding a solution to the alternate black problem, and we're using that as an upper bound. But if f prime is greater than f for all values, wouldn't the minimum f prime also serve as an upper bound?
No, it wouldn't. Let me explain why. So, okay. So once again, your question is that we have this x and we have some function let's put here, and we are saying that the maximal value for this for the original problem is over here. So this is the value of it, and there is a relaxation that says something like this, and the optimal value of the relaxation is going to be here. However, not any value of the relaxation is going to be above this point. For example, this value over here is going to be lower than this value. Does that answer a question? Yep.
Depending on the you might be able to hit proposition 2.
Yep.
You might miss it entirely.
Absolutely.
Drew like you drew f of x, but like just which is where the optimal solution for the right there, and then you would draw the bit, and you have to do.
Exactly. Yeah, that's a very good point. And a function that has this property that it is actually like the relaxation with this function would actually give you the optimal solution according to proposition 2 is called the convex hull of the function. So basically, like it is a very related notion to the convex hull of the set. If you remember, we were talking about having a non-convex set And we said that something like this is going to be like the smallest convex set that contains the original set is the convex hull of this set. A function of this type, is called a concave function, or if we were to minimize everything, then we will be talking about it like if we were to minimize everything, then we would have an optimal solution here, and a convex envelope over the convex hull of this function would be the like a convex function that the smallest convex function that lower bounds the original function. In this case, it would be a function of this sort. And the closer your relaxation to the convex hull of the domain and the objective function, the better it is, and the better the chance that you will end up with a relaxation that will solve your original problem. But constructing convex hulls is extremely hard. It's just very difficult. Sometimes it's just easier to solve the problem. Does it make sense? Cool. Those questions are great. Give me more of them. Cool. All right. Combinatorial relaxation. Okay, so this is regarding the linear relaxation. There is an example. There are two more examples in the book. Please pay attention to them if you ever stumble upon a problem. Combinatorial relaxation is, as both from definition, it's a combinatorial problem that is a relaxation of the original problem. We will see a particular example. Some combinatorial relaxations are better than the others. So if you came up with if you came up with a linear relaxation, all of the linear problems are quite simple. So if you ended up with a linear relaxation, most probably you can solve it efficiently. However, if you ended up with a combinatorial relaxation to your original problem, it still might be hard. So if you have ended up with a combinatorial relaxation that is hard, you still might drop constraints there in order to make it even easier, make it easier, and that thing that you will end up with will still be a relaxation. So that's a valid thing to do. More examples of it in the section 2.3. We'll go over just one of them. That is dealing with traveling salesman problem. However, we haven't introduced traveling salesman problem just yet, although it is a very, very important example. So first we go and introduce the problem, then we introduce the formulation, then we relax the formulation. That's what we're going to do for the next half an hour. Any question regarding what we are doing right now? You do remember the combinatorial relaxation. It's a linear programming problem over a set of subsets, right? Introducing the traveling salesman problem. There are n cities for a salesperson to visit. The time taken to travel from city I to city J is Cij. So we have a network. We have a graph consisting of cities. They are connected, and we have Cij that like a weight that tells us how much it takes to go from city I to city J. We need to create a travel itinerary so that we visit each of the location only once and then return to where we have started, while minimizing the total travel time. Okay, so the variables here are going to be Xij, and Xij is going to be equal to 1 if a salesperson goes directly from city I to city J, and Xij is going to be equal to 0 otherwise. So basically, what we are getting here is we are trying to construct a cycle, this sort, for example. And if an edge does belong to the cycle, then the corresponding Xij is going to be equal to 1. It's going to be equal to 0 otherwise. The objective function in this case is a summation over all xij of correspondingcij's. So this is a linear function of xij of the variables, and the constraints are the most interesting things. The salesperson must arrive once at each city, which is represented with this constraint right here. So our summation over all j's is over xij's is going to be equal to 1, which means that well, our edges here are actually arcs, right? They are directed. We are assuming that we have an arc that goes this way and an arc that goes this way, and we know that on our path for each node I, there is a single arc inside our path, inside our cycle, that points into the node, which is what the first constraint is representing. The second constraint is that the salesperson must leave from each city. So this constraint is saying that for each node I, there is a single arc that goes from this node I and goes to some other city. In this case, anyway, it's going to be a city I that we go into from city J. Are these two constraints enough? So if we put together this optimization problem, first thing that we can mention is that this does look very much like an assignment problem. If you remember the formulation for the assignment problem, it was sometime before. So this was the formulation for the assignment problem. We also had the two constraints that the summation is going to be equal to 1, and xij was from 0 and 1, and we had a linear objective function. Just to remind you what the assignment problem was, we had special agents, and we needed to assign them, and they needed to carry out missions. So this formulation that we have ended up with is suspiciously similar to the formulation of the assignment problem. Here it is. The problem here is that the optimal solution to this formulation of traveling salesman problem can look like this. As you can see, there is no single cycle that goes to all of the nodes. Instead, we have separated our entire problem into subcycles. Our entire graph is now separated into subcycles. So this is not exactly what we wanted, because we cannot really start from two points simultaneously. So we need to, this implies that we have not listed all of the necessary constraints that we would need in this problem. There are two options for us to get rid of this subtours. This is called subtours. To avoid them, we can the first constraint is the cut set constraints. For each subset, we would like to leave it at least once. So whatever subset of the nodes we are choosing, for example, we have chosen this subset, we need at least one edge that leads from this. Like we need at least one arc that leads from this subset, and this must hold for all of the sets, for all of the subsets that are not an empty set, and which are not the entire graph. This is one way to tell. Like obviously a subtour subtours like this would not satisfy this condition, because we can just take the set of 1 and 10, the nodes 1 and 10 into a subgroup, into a subset, and there's no arc that leads from this subset. So this would not satisfy this condition. This would violate this condition. So we would not have the previous solution as a feasible solution. The other subtour elimination constraint is the following: for each subset of the nodes that contains at least two nodes and not more, like does not contain all of the nodes, we need we need them to have edges between themselves. The number of edges within the group must be not enough to form a cycle. This would essentially suffice to eliminate these constraints. Again, if you take, for example, those three nodes, the number of arcs that suffice to let them form a cycle is 3, and we can see that there are three arcs, which implies that if we were to add this condition over here, the former picture would not be a feasible solution. It doesn't really matter which one you add. I mean, it is application dependent. There's no like general answer to the question of whether one is better than the other. Both of them works. Right now we can settle on one, and this would be our eventual formulation of the traveling salesman problem.
And the other, either subtour elimination or concept constraint, they require, they like go over all the different subsets, like the
Exponential.
you can just think this into like a subtour,
Yeah, so it is exactly the thing. It is a very big problem, and that's why traveling salesman problem is actually quite a difficult one. What we're gonna do is we're gonna build like a combinatorial relaxation to relax this problem. But you're right. Like, first of all, when you're writing it down, there is a way to express that you that you mean as a particular constraint for all subsets. So you don't need to write it down physically, but eventually it will turn into an exponential number of constraints. There is
Is it hard, this problem?
Oh, it is. Yeah. So this is like traveling salesman problem, unlike assignment problem, is a very hard one. However, since it is a very practical, also it is a classical problem from industrial engineering. So it happens a lot everywhere. So we still need to solve it, even though it is NP hard. And how people deal with this exponential number of constraints is the following thing. I really hope that we can get there at some point during the class. It looks like we will have time, but I won't promise it. There is an approach that consists in sequential adding of new constraints as you solve the problem. So you start the solution with some very simple formulation, and then you optimize over this formulation. You find a feasible solution, and then you realize that this solution, there's a systematic way to realize which one constraint out of this system of constraints this solution violates, and you add a cut. You prohibit to enter this region, and then you resolve the problem and find another solution, and then you add another cut. And you end up just adding cuts, and you never really deal with all of these constraints simultaneously. You end up just generating new constraints on the fly. This is a very advanced technique called it is part of the branch and cut algorithm that we get into later. Yep.
Does that generate an exponential number?
It could. In the worst case, it does, but often it doesn't. So that's a relief. Any other questions here? Cool. Okay. So an example of a combinatorial relaxation. An example of a combinatorial relaxation would be to just drop this, all of these exponential constraints. You instead of formulating, so on the top, sorry, on the bottom, we just put in like in a precise, like in a compact form, the formulation for the assignment problem. We are minimizing over all of the subsets T of a set A, the set of arcs. The summation over the entirety of Cij. So the objective function is there, and then we just require for T to form an assignment. T forms an assignment is actually just this couple of constraints. So this is this is an assignment problem put into form of a combinatorial problem. On the top, you can see a formulation of the traveling salesman problem as a combinatorial problem as well. And we can see that we can go from one on the top, which is very hard, to the one which is on the bottom through a relaxation. So by just dropping this constraint, we will get the easier the easier combinatorial relaxation, the easier combinatorial problem, which is going to be a relaxation for the original one, because we dropped constraints. So here I assume obvious that when you drop constraints, you get a relaxation. The incomplete formulations. Yeah. So like we have dropped them before by mistake. Now we do it on purpose. Any questions? Huh? Yeah. So because now we're talking about minimization problem, it goes the other way around. It is still a dual bug. Sounds good. Any other questions? Anyone needs rest? We're good. Okay. Okay. So now we have looked at two types of relaxations. The first one is, by the way, I didn't mention it, but the next time we're going to be talking about traveling salesman problem specifically, and we're going to see how to input that into solvers and how to make them solvers. So it's coming. The Lagrangian, the third type of relaxations is the Lagrangian relaxation. It is more like, first of all, it is highly generalizable, and it's applicable pretty much everywhere. And the second thing is that it can be done not only to integer programming problems or linear programming problems, but to virtually any kind of problems. Let's say that we are dealing with a problem of maximization of an objective f0, subject to a system of constraints that are given through functions fi, and also a constraint that x belongs to some capital X set. And in this case, we are saying like we are saying that these are the end conditions over here are the conditions that we are going to be relaxing, or in other, if someone also says dualizing, we will see why. So we are dualizing this constraints, meaning that we would like to obtain a new formulation that does not have this constraints. However, we like if we just drop them, that won't be very good, because I mean it's probably they probably put there on like for some reason. So dropping them is not really an ideal scenario, and we would like to account for them somehow. To account for them somehow, we can add them to our objective function. Let's say that we have put together a number of coefficients, like weights, called u, and we are adding to our objective function a term that depends that consists in multiplication of u and this function fix. So u here are actually parameters. So we are not optimizing of them. We are only optimizing over x. So it's fine even if we are talking about linear functions. This function over here is still linear in X. This kind of problem is called the Lagrangian relaxation of the prime. So there's a proposition 10.1 that you can look up that is telling us that for any u that is non-negative, we have the inequality that the solution to our original problem is actually going to be less than or equal than the solution to our relaxation, right? Which like if we are considering maximization problem, would give us an upper bound, which is the dual bound in our case. So this is the mechanic of like how exactly you perform a relaxation. Let's take a look at an example. What happens if we apply this technique to specifically a mixed integer programming problem? Let's say that our like part of our formulation consists in a system of linear inequalities of this type, dx less than or equal than d. The rest of the like linear inequalities and possibly the integer constraints are actually hidden in this domain X. So dx less than or equal than small d is a system of m complicating constraints that we would like to get rid of. We introduced the vector of parameters q, and we so this inequality can be written as minus dx plus d is greater than or equal than 0. And in this case, it will like basically our function fi is gonna be this function over here, or the same thing, this function over here. So we can just multiply our vector by our vector of parameters q by this vector function d minus dx, and add this into the objective function. This is called the Lagrangian relaxation of an MIP, of a mixed integer programming problem. Any questions regarding the mechanics of how you do it? Yep.
Yeah. So for adding all the constraints and things, that increase the likelihood that it will be.
Yeah, absolutely. That's why you like you need to do it carefully. Obviously, you cannot just do it for whatever purpose. However, if you are designing this U carefully enough, so that they are large but not too large, you have zero chance of getting out of bounds of this constraint d minus dx, just because it will cost you so much to get out of those bounds, because every time you get out of those bounds, you multiply that violation of the bound by a very large number u, so that it ends up being a very big penalty to your function, and therefore there's a value for u, so that the optimal solution of the original problem is actually coincides with the optimal. Like, I mean, sometimes there is a value of u, but it's not always possible to find this value of u. But if you design it carefully enough, it will not end up it is an unbounded problem, but its solution belongs to a compact set. Any other questions? That's a good one, by the way. Any other questions? Okay. Let's take a look at a particular example. Let's have a problem: maximization of 7x1 plus 8x2 plus 3x3, subject to two different inequality constraints, and x belonging to a set of integer values. So the Lagrangian relaxation for this case, like in order to construct one, we would need to first express what d minus dx, like how to express it. First of all, so we have like our d is a vector of two variables, 32 and 107, and that vector is going to be multiplied by u1 and u2, and you essentially what you're doing, you're taking this 32, putting it here, and you're taking the rest and multiplied by -1, putting it over here. I suspect that might be parentheses missed over here, and the same here, and the same thing is happening to the second part. What we end up with is the Lagrangian relaxation of the original problem. Okay. So the theorem 10.1 tells us that solving the Lagrangian dual for the mixed integer programming problem provides the same bound as solving the problem where we have convexified the set X, like the rest of the domain that we did not dualize, which is kind of a cool thing, because if you have dualized all of the inequality constraints in your problem, and the rest of the solution X is, for example, you're saying that X is equal to Z, for example, 3 in the previous problem. In the previous problem, we have dualized everything. The only thing we have left out is X belonging to Z3 plus. So we are saying that solving this problem is actually the same thing as solving a convexification of X. What in case X is Z3 plus, the convex hull of Z3 plus is just R3 plus. Therefore, for the previous problem, for this problem, the solution is going to be as good as the solution to the linear relaxation. So it's really not that. Okay, I need to say here that we are like this theorem is talking about the dual, which we will cover on the next slide. So this theorem is actually talking about U being specifically designed to represent the dual problem, which we're gonna be covering next. So let me skip to the next slide, and then we will return here. So beyond the relaxation, even though there are multiple relaxations available to us, there is one other quite a powerful technique called the duality. The main difference between the bounds, the dual bounds provided by the relaxation and the dual bounds provided by duality is that in the relaxation we need to solve the problem in order to obtain a bound. In duality, we don't need to solve the problem in order to obtain a bound. It is enough for us to find a feasible solution. So, related to one of the questions I've been asked, any feasible solution to the dual problem provides you with a dual bound for the original problem, unlike for the relaxation. So how to define a dual problem? We are saying that the two problems, one of maximization of certain objective functions subject to X belonging to a domain, and the second being a minimization problem of an objective with over a completely different domain, possibly a completely different domain. These two problems are forming a weak dual pair if the optimal value for the original problem is like if we are putting them in this order, then the value of the objective function of the original problem, of the primal problem, is less than or equal than the value of the objective function of the dual problem for all feasible points of the original problem, of the primal problem, and the feasible points of the dual problem. So this is basically saying that every feasible point is a dual bound. And then we are saying that the bound, the duality is strong. They're forming a strong dual pair if the optimal solutions to both problems coincide in value. Any questions regarding the definition of duality? No. So we are defining the primal variables. The variables for the original problem are called the primal variables, and the variables for the dual problems are called the dual variables. So there are x and u. The difference between the optimal value of the primal problem and the dual and the optimal value of the dual problem is called the duality gap. So if it is 0, then the problems form a strong primal dual pair. We will turn to how to construct dual problems in a minute. Are there any questions regarding the main definitions? Okay. An example. So let us take a look at the matching covering problem and we will see what it means to be primal dual pair for this problem specifically. So if we are given a graph consisting of, like, for example, this one, consisting of vertices and edges, we are saying that a subset of the set of edges M is a matching if it is a set of disjoint edges. For example, in this case, this set of bold edges is a matching, just because they are disjoint. A subset of the set of vertices is a covering if it is a set of nodes that such that for every edge E there is at least one element from the covering R that is the border of the edge, meaning that it is an endpoint for this edge. In this particular example, the set consisting of the node 2, node 3, node 6, and node 8 is a covering, just because for any edge, whatever edge you pick, there is a node here that is an endpoint, and that belongs to the covering. Is it clear? Is the problem formulation clear? Okay. The maximal subset is one that is not contained in any other subset from the bag of subsets. So there is this two definitions basically just explain you the difference between the two terms. One is the maximum, and the other is maximal. Maximal is the one that is not contained within any other. For example, if you have subsets and you have like a set here, this one is a maximal just because it's not contained in any of the other. And the maximum is something of a largest cardinality. For example, this one is the maximum just because it's big, while this one is the maximum. Any questions? Cool. So we have two problems here. The first one is the maximum cardinality matching, meaning that we want to find a matching that has most of the as many edges as possible. The other problem is the minimum cardinality covering. we would like to find a covering that has a smallest number of vertices as possible. And first of all, you need to note that one is maximization, the other is minimization. And the proposition 2.7 is telling us that the maximum matching and maximum covering form a weak dual pair, meaning that every feasible solution to one is a bound to another. It is important to also to say that, well, if we were to take a look at the definition for the dual problem, you can see that an optimal, like a feasible solution for the dual problem limits the optimal solution to the primal one, but it also works the other way around. So whatever feasible solution for the primal problem you have, it bounds from below the optimal solution to the dual problem. So like having primal dual and dual primal, like the dual is a dual to the prime in a way. So it's interchangeable. Therefore, we are not really saying that one is primal, one is dual. We are talking about primal dual pair. Yep. Yep.
I was just wondering if we could follow along with these.
Yep. Let me make them available right now. I was thinking about, by the way, sometimes I'm just I'm updating the lecture slides. If everyone has Overleaf account, I can just share with you the slides, and I will not have to update them all the time because it takes time to download and upload. Okay, cool. I'll do that then. Can you please go to my website and tell me if it worked or not? You just need to click the lecture slides. It worked? Okay, so say it again. Yeah, it's an Overleaf. Just it's not on big courses yet, but I will figure it out later. Just use my website for now. Okay, sounds good. Cool. So by the way, I wanted to ask this for a long time now. Did you guys are you familiar with LP duality at all? Okay, so basically everything I'm so speaking about right now is actually not as new to you. Okay, that's good. I will still kind of assume that you don't, but it's very helpful to understand that we understand each other. Cool. So let's take a look at the maximum matching and minimum covering forming a weak dual pair. So how to show this fact? Well, first of all, if M is a matching with edges I1, J1, and so on, like with k different edges, then there are two k nodes that are distinct, and any covering by nodes R must contain at least one node from each of the pair IS, JS. Therefore, since any covering must contain at least one out of each pair, at least one node, not one node out of each pair, it means that in each covering there must be at least k nodes total. And if we are speaking about, like, since M was a matching, therefore we are saying that if we have any matching, virtually any matching, and we have virtually any covering, no matter what covering it is, there is an inequality between the cardinality of the two sets. So this shows that like just by definition that these two problems form a weak dual pair. However, if we are familiar with LP duality, we can also say that we can use the following proposition: a dual of a relaxation is a dual of the original problem, right? How to understand this? Let me write the picture so that I make sure that you remember this. So let's draw a relaxation. We have this f. We have an objective function f, and now we first of all we extend the domain x dash, and we have a different objective function f dash. We are talking about maximization problem. This is our original problem and the relaxation. And now we know that the any solution to a dual problem is not going to be above the solution of the original of the relaxation. Sorry, any solution, any feasible solution to the dual of the relaxation is going to be above the any point on the relaxation. So we have some other problem here that is a dual problem of this one, such that any feasible point is going to have a bigger value than any of this points. And since it will have a bigger value than the optimal solution of this relaxation, then it will have an optimal solution to the relaxation is definitely greater than the optimal solution of the original problem. We will have that any point on the objective function of the dual for the relaxation is going to be above any of the points of the original problem, any of the objective values of the original problem. Is everything clear here? I was trying to prove the proposition, at least show the intuition behind. Yep.
Like using the same logic, those are the original problems not
Absolutely not. It could be that the dual for the original problem would have values somewhere here, and then the optimal solution for the relaxation would be greater than some of the points. So if we use this proposition and apply it to the question regarding matching and covering, we will see that do I have it here? Okay, yeah. So we will be able to write down our matching and covering problems as linear program as integer programming problems, and then dualize them and apply the previous proposition. So let's write them down as integer programming problems. First of all, we need to define the incidence matrix of a graph. And incidence matrix of a graph is a binary matrix that describes its structure. There are two types, like two main types of incidence matrices. One is the node incidence matrix. The other one is the edge node incidence matrix. The node is a matrix where you have nodes on the axis, on the like on both dimensions of the matrix. You have nodes, a node I and node J. On the intersection between the node I and node J, you have a value 0 or 1 that is telling you if there is an edge that connects the two nodes or not. The edge node incidence matrix has edge on one of the dimensions of the matrix, and it has exactly 2 ones on each row in this particular example. That is telling you which 2 nodes it connects. So both of them exactly like uniquely capture in a way uniquely capture the structure, because they're actually like obviously permutations of them would still give you the same kind of graph. So if you're given the node A edge incidence matrix of a graph G, then the following IP formulations for the maximum matching and minimal covering hold. In the first one, you have vector 1 of 1s multiplied by x, which is counting basically the number of zeros and counting the number of 1s in the vector x. In this, the other objective function is constructed exactly the same way. We are having the vector of y's that is indicating to us if we have put a node into a covering or not, and the vector x is indicating if we have put an edge into matching or not. And then in one case, so like in order to indicate that this is indeed a matching, we need to make sure that ax is less than or equal than 1. And in order to indicate that it is a covering, we need to make sure that ya is greater than or equal than 1. The one thing tells us that the things are independent. The other one is making sure that we have covered everything. And now we just need to make sure that the vector x and the vector y, vector y are both integral. Moreover, they are binary, and this will lead us to integer programming formulation for both matching and covering problems. And now we just need to write down LP relaxations for both of them. So basically, we would just drop this constraint of binarity, and after that we will like after that we would need to dualize one of them. For example, if we dualize the problem ZL, like the linear relaxation of this problem, then we would get a problem that exactly coincides with the W. So therefore we can see that and W is a relaxation for WLP is a relaxation for W. Therefore, between Z and W, there is a primal dual pair relation. Any questions here? I can go into more details if that's of interest. Guys, any questions? No questions? Okay. Okay, so this was an example of duality. We did not really construct it. We just took two different problems, and we have shown that they are forming a primal dual pair. Let's take a look at this as a systematic way to construct dual problems. And such a way is called the Lagrangian. Like one way to do it is using the Lagrangian relaxation that we have seen before. The corresponding dual is called the Lagrangian dual. So we have seen that relaxation is giving us different upper bounds ZU depending on the value of the vector U that we come up with, that we design. We only need U to be a non-negative vector. So if we aim to design the best upper bound that we can possibly get out of this Lagrangian relaxation, a problem that we will end up with will have this form, where we are minimizing the upper bound on the original problem, which is ZU, over all of the different vectors with the non-negative values. This problem is known as the Lagrangian dual problem, and indeed, since any kind of for any U, the optimal solution. You remember there was an inequality that was making a relation between Z and ZU. Right. Where was it? Right here? No. Right here. We have mentioned that Z is always less than or equal than ZU. Therefore, every feasible solution, for every U, the value of the objective function will be greater than or equal than Z of interest. Therefore, the Lagrangian dual problem is indeed a dual problem. For example, if you remember our example from constructing Lagrangian relaxation, we ended up with a problem of this form right here. Now we would need to just substitute it into this framework in order to obtain a problem of this form, which is going to be the Lagrangian dual of the original integer programming problem that we have been dealing with, this one. So the Lagrangian dual of this problem is in fact this one. There are a few interesting properties of Lagrangian dual that are concerned with its solution mainly. So the Lagrangian dual is a convex problem, saying that ZU is in fact a convex function, and U greater than or equal than 0 is obviously a convex set. Therefore, the Lagrangian dual is a convex problem. However, which implies that we can use first order methods to solve the Lagrangian dual problem, meaning that basically there are plenty of heuristics that would theoretically allow us to reach the global optimal if we solve the problem of Lagrangian dual to local optimality, then it would result in the global optimality of this problem. And the problem of local optimality is normally not too difficult. However, there are bad news which consist in the fact that Z of U might be non-differentiable, and moreover, it might not have a compact description at all. So Z of U might be just a very complex function that consists of multiple, most probably is going to have a form like this, and the number of this linear parts is very large. Yes, there's a question. Yep.
So there's like a almost infinite number of Lagrangian relaxations we create, right?
Yep. Exactly.
And we have the Lagrangian relaxation, and then to find the best upper bound. Because It's because we know that the Lagrangian relaxation is always greater than equal to the original problem, right? And to minimize the parameter use, basically minimize over the set of like relaxations and the best parameters of U that minimizes that one. And this best one is the Lagrangian dual.
That is going to be the solution to the Lagrangian dual. Exactly. Yeah. So the problem of minimization that you're talking about is called the dual problem. The problem of minimization over over the space of Lagrangian relaxations. The problem of minimization over the space of Lagrangian relaxations is the Lagrangian dual problem.
And then with all the other relaxations, even not like the not suboptimal ones, are still dual.
They are still the feasible solutions to the dual problem, but they're not necessarily the optimal solution to the dual problem. Let me draw it. So let's consider. So there's the primal problem, X F, and there is a dual problem that has a different domain U and different objective function. And we are saying that each point from this U would give you a relaxation over this set, which in this particular case, so like if the value is here, the value of this point is this one, and therefore the optimal solution to the relaxation must be on the same level, which is here, for example, and therefore the solution that the relaxation that corresponds to this point is going to have that something like it's going to have a form of a function like this. So we are saying that as we vary the points U over this set, we are considering different relaxations that will have different optimal values, and we stack this optimal values into this function, and then we optimize over this function over the space of Lagrangian relaxations in order to find the best relaxation that gives us the lowest value.
We try to minimize the relaxations so we have the lowest one. That means that we want that because best or like that way the function is capped at minimum.
Yeah.
And so the one those like extra mountains on the right, like those are the rules.
These ones, these are the Lagrangian relaxations, and this is Lagrangian dual, which like each feasible solution to the Lagrangian dual corresponds to a single mountain over on the right, a single relaxation.
Okay.
Does it?
I was having difficulty about which one was.
Yeah. I understand, because it's really like it's a really subtle, and I think I spent a long time realizing it in back in my days. So if you have any questions here, if you don't understand this picture, please do let me know, because there's no other way I can help you. Sounds good. Yep.
That's a different question. When we use like a lot of engineering duality in IAR 162, the method for creating the dual of a linear diagram was essentially using the constraints in the objective function and then using the coefficients of the objective function. Where does that fit into this process of creating duals, and is there any guarantee that that dual will be?
Yeah. So actually, a linear dual is a special case of the Lagrangian dual, and the process of creating U constraints is basically described in this process of going from the original problem to the relaxation of it. Basically, what you are doing with this dx less than or equal than d, you're multiplying the inequalities by non-negative numbers, and then you add them up. And that is like your new kind of constraint, that instead of putting into constraints, you put it into objective function, which is precisely what you're doing when you're dualizing a linear programming problem.
I remember when we made those dualities, there was no notion of selecting a U. You just kind of took the coefficients that were in the objective function, you just constructed new constraints. So is some U being implicitly selected if you create actually new constraints?
I have to clarify here. So when you were essentially you're multiplying your, so to each linear inequality there was a non-negative coefficient that corresponded to that, right? Which is called the dual variable. And how did you denote that? Like what was the like lambda or something? So that lambda is this U. They are the same. And this U is called the dual variable in the Lagrangian dual. And if you are doing this, like this entire procedure of dualizing a linear programming problem, what you will end up with is the linear programming dual with the dual variables denoted as U. Does that sound good? Cool. Yeah, so I said that actually, even though the Lagrangian dual is a convex function, it's not always easy to optimize over. Most commonly it is. However, Lagrangian dual is only weakly dual unless special conditions are satisfied. For example, like Sayers conditions and other. I just have to say that, like, since like if you have a hard problem and then you get a dual of that, it's either very hard to optimize, or its solution will not give you the exact bound. Will not give you the exact same value as the maximization of the original problem. On this picture, you can see that the optimal value of the dual is here, which is like on this level, and the optimal value of the original objective function is, for example, here, which is much lower. And this is what's going to happen for difficult problems most of the time, with this difference between the two values being called the dual gap, the primal dual gap. Okay, so yeah, only weakly dual is guaranteed to hold, and however, this gap is possible to close. It's possible to close this gap if there are conditions that satisfy it. You can read about it. I don't think there is much about it in the book, but there is information about it on Wikipedia if you ever stumble upon this kind of stuff. One thing that I wanted to comment on is that there is a dual problem to any mixed integer programming problem that has this gap being closed. So you basically solution to the original problem is equivalent to the solution of the dual problem, and so there is another problem that forms the strong duality pair with any mixed integer programming problem, and this dual is called the superadditive dual. It does not really talk about, oh my god, it went out of bound. Anyway, I just wanted to say that it is still a very hard problem, because it optimizes over the space of super additive and non-decreasing functions. What is a super additive function? It is a function that at 0 it has a value 0, and if you add this function at two values u and v, the result of the addition must be less than or equal than the result of the function at the addition of these two values. This is quite a special property of a function, and it is not easy to enforce this property. A non-decreasing function is a function such that for any u and v that are relatable, that you can basically compare them component by component. If u is less than or equal than v component wise, then f of u must be less than or equal than f of v. So if you have a function that satisfies both conditions is called the superadditive and non-decreasing. And bright examples of superadditive and non-decreasing functions are a function that gives you the floor of a number. Like for example, the floor of 0.5 is 0, the floor of 1.8 is 1, and so forth. So it's just a function of this form. Anyway, so you got the point. It's just a step function. Another important example is the result of a maximization problem, of an integer maximization problem. It turns out that it is superadditive and non-decreasing in D. So this, like, if you vary D, if you vary the right hand side, then the corresponding value, the corresponding optimal value of the integer programming problem will give you a function that is superadditive and non-decreasing. This is not an obvious fact by itself, but you can prove it. And the statement is that for a feasible IP with a bounded LP relaxation, there is a strong duality between the problem of integer programming problem and the problem of optimizing over the space of superadditive non-decreasing functions. It is kind of a neat result, which is telling you that, well, there is a result like this that bounds a primal linear programming problem and the dual linear programming problem, and saying that there is a strong duality that holds between them. So you would expect that something similar would hold for integer programming problems as well, just because of their linear structure, and it does hold, but in a way so that it becomes unbearable to like this dual problem is not really useful in any practical way. It's just an interesting fact that there is a matching dual for integer programming problems if you ever need one. We will not be talking much about this, just for your breadth of understanding. There are some references regarding the duality theory that I put down in the lecture slides. What we're going to be doing next lecture is we're going to be looking at traveling salesman problem, how to put it down into code, how to make it work, and after that we will turn to primal bounds and see what is possible to do there when we are trying to obtain one from the side. Thank you very much for attention. If you have any questions, let me know. Please stop by the discussion section tomorrow, and there is office hours tomorrow. We'll be expecting everyone. See you later.